Now, keep lined up on the center line of the runway. Keep those wings level. That's it. You're doing fine. Well, we did land a little hard that time. Maybe it'd help if you understood better just how air affects a landing airplane. In other words, let's bone up on basic aerodynamics. It's important that you know how an airplane flies. Many accidents are caused by lack of understanding basic aerodynamics. That's why we have ground school, to get pilots to understand the fundamentals of aerodynamics and make our flight training hours more effective. It's all concerned with answering the question, how do airplanes fly? From a pilot's viewpoint, the aerodynamics we need to know is relatively simple. It's enough to know that this whole field of physics called aerodynamics is largely concerned with the motions of air and other forces, and how these forces relate to the mechanics of flying. We don't need to get involved with the mathematical formulas with which aircraft designers deal. But if you asked an aeronautical engineer to answer our question of how an airplane flies, he'd say quite properly that, very simply put, it's primarily because lift equals the coefficient of lift times 1/2 rho, the atmospheric density factor times the velocity in feet per second squared times the total wing area in square feet. Of course, you don't have to be a graduate aerodynamicist to fly. But you do need to know some of the principles of flight theory which will apply to any aircraft you fly. It's much the same thing as knowing what a road is and how a car is operated in order to become an accomplished driver. But unlike a road, the motion of air is hard to visualize. Perhaps that's one of the reasons why aerodynamics seems difficult at first. Air, of course, is simply a mixture of gases. We live at the lower layer of the atmosphere. This not only makes it possible for us to breathe, but it is also the air that enables us to fly. All we really need to know about air right now is that it has substance, that it is denser near the Earth and gets thinner at higher altitudes. Thus, it exerts force when it moves. And as far as air being invisible, the aerodynamicists have come up with a way for us to see it in a smoke tunnel. It's done by drawing streams of smoke into the air. If we can see the air, then perhaps it will help us answer our beginning question: how do airplanes fly? We'll start with a double-winged model in the airflow. The action of the air between the wings will demonstrate a basic principle of aerodynamics. Now, by animation, let's study the airflow in greater detail. First, note that its pattern suggests it is passing through a tube-shaped device. Next, notice that the entrance and exit of the device are the same size. We can measure the openings and find that the ends are each 10 square inches. The middle part is squeezed, creating a throat of 5 square inches. Now, if we direct smoke lines through the device, its pattern will show that something happens to the air where it goes through the narrowed part. What we find is that when the airspeed is 100 miles an hour at the entrance of the device, it is also 100 miles an hour at the exit. Yet at the same time, the speed at the narrow part is considerably higher. It can easily be understood, therefore, that the air increases in speed as it passes through the smaller opening. But the interesting thing is that in order for the air to go at the faster speed through the narrow part, something has to balance this change in velocity, this speed difference. What changes is the air pressure in the narrow part. This pressure is significantly lower than the pressure at either end. But what does this have to do with flying? If we cut the model in half, we would have a profile similar to an aircraft wing section, called an airfoil. You can see how helpful it would be to lower the pressure over a wing. Why? so that the comparatively higher pressure under the wing would push or lift it into the area of lower pressure above the wing. That's part of how an airplane flies. Some of today's wings have what is called a symmetrical airfoil, with the same curvature on both sides. In level flight, this design will tend to equalize the pressure on the top and bottom of the airfoil. But watch what happens to the airflow when we incline the airfoil a few degrees. We have caused a low pressure on top of the wing. This creates a pressure difference between the top and bottom, giving us lift. The airflow striking the fixed wing airfoil of an aircraft, or the aircraft itself, is called the relative wind. The direction of the relative wind is always opposite to and parallel with the flight path of the airplane. In level flight, therefore, the relative wind and the flight path are horizontal and parallel. The center line, or chord line of the airfoil, however, even in level flight, forms a small angle with the flight path. We call this angle the angle of attack. We have given it the symbol alpha. What happens when we increase the angle of attack? When we increase alpha, we increase the pressure difference. This creates more lift. But there's a limit on the lift. See what happens to our smooth flow when we increase the angle of attack further. This is where the stall begins. If the alpha angle is increased even more, lift will decrease rapidly until there is total stall, with a great loss of lift, and turbulence so great it may buffet the airfoil. As a pilot, you'll need a healthy respect for stall. The three aerodynamic principles we've just seen, lift, angle of attack, and stall, are so important we ought to put tags on them. This symbol might serve to remind us of the principle of lift. Lift is the flying principle that, as air is accelerated over an airfoil, it reduces pressure and thus overcomes weight. Let's tag angle of attack with an angle and the Greek letter alpha. As you recall, alpha is simply the angle formed between the relative wind and the chord line of the airfoil. But its importance is in the fact that even small variations affect the amount of lift. Stall might be represented this way, with emphasis on the fact that the air flowing over the top of the airfoil ceases to follow the upper curved surface and breaks away in eddies of air. Stall, of course, is the result of an alpha so great that the air can no longer flow smoothly over the curved top surface of the wing. Stall for many airfoils begins at about 15 degrees. Why all this talk about airfoils? Well, as we've said, wings are airfoils. But note the other airfoil shapes: the vertical tail, the horizontal tail, even the propeller, and in a sense the fuselage itself. All are aerodynamic shapes. The design of an aircraft is determined by a careful consideration of many aerodynamic shapes and how they totally respond to the principles of lift, angle of attack, and stall. And because these airfoils are so important aerodynamically, let's get to know their language. To begin with, they have a rounded leading edge and a pointed trailing edge. The center line from the center of the leading edge to the point of the trailing edge is called the chord line. We also speak of camber of an airfoil. Camber refers to curvature. We've spoken of the forces of lift, angle of attack, and stall that work on an airfoil. But there are two others. First, we need a force to make the plane go forward and create the relative wind. This is called thrust. Since thrust is another of the major aerodynamic forces, we'll tag it with a symbol representing a propeller and an arrow. thrust is generated by an engine which exerts the force to move the aircraft forward. Aerodynamically, the airfoils of the propeller blades form lift or low pressure in front of the blades, pulling the propeller forward. But what about thrust in the case of jets? The exhaust gases and air are pushed out of the exhaust with such tremendous action that the balancing reaction thrusts the aircraft forward. But when the airfoil, or any object for that matter, is thrust through the air, there is a retarding force of air resistance and inertia. We call this drag. Let's represent drag as a backward arrow and a parachute. Drag, too, is one of our major aerodynamic forces. Now we've come to the point of examining all the forces acting on an airfoil in flight. Lift, we know, is what holds up the airplane. Putting it another way, it overcomes the weight of the airplane. Thrust is what moves the airfoil ahead and overcomes drag. When an airplane is flying straight and level and is not accelerating, these forces are in balance. Thrust equaling drag and lift equaling weight. But we don't just fly straight and level. We have to get up there and back down, and we want to move around. Suppose we increase power. We increase thrust. And while it is out of balance with drag, speed will increase. But drag will also increase with speed until these forces are in balance. By increasing the speed, we also increase the lift capability of the aircraft, because more air is flowing over the airfoil. The lift is maintained equal to weight by changing the angle of attack with speed. In steady level flight, all forces are in balance. Thrust equals drag, and lift equals weight. And this forces in balance relationship is so important a principle of aerodynamics that it too should have one of our tags. Let's make it with 4 equal arrows for lift, drag, thrust, and weight. But let's not leave our discussion of these forces without noting that they may be acted on or influenced by outside factors. As we've said, an airplane is a total of many aerodynamic shapes, but some of these are variable. That's how we control flight. The vertical tail has aerodynamic characteristics due to its shape. These cause it to move the fuselage from side to side as the rudder is deflected. This smoke tunnel model shows how control surfaces work. When the hinged surface is moved away from the streamline position, we increase camber. This gives us a controlled pressure difference which produces a desired force. Elevators are hinged surfaces connected to the horizontal stabilizer. They work in the same way as the rudder. Moving the elevators varies the angle of attack of the airplane. This small control surface is called a trim tab, and it is an aerodynamic device used to ease the pressure on pilot controls by creating enough lift in the segment to hold the control surface in position aerodynamically. Ailerons, too, are movable surfaces. They are placed outboard toward the wingtips. As they are moved, they vary the airfoil, increasing the lifting force on one wing while decreasing the lifting force on the other. In some aircraft, there are other devices to vary the aerodynamics of the wing. Most of these are high-lift devices, such as flaps, which reduce the stall speed during landing and takeoff. Perhaps you'd like to see the aerodynamic results of the total airplane in the smoke tunnel. Starting at the midline of the fuselage, we slowly move the smoke lines. Note how the shadow of the smoke line moves across the top of the wing. You can see how the airflow is affected by the plane structure. If you look closely, you can see how increasing alpha increases the lift. But what happens to the total aerodynamics when we increase alpha beyond that recommended? You guessed it, stall. Curiously, many inexperienced pilots tend to attempt to raise the nose of the stalled aircraft because of the sensation of falling, which of course increases the angle of attack and brings on deeper stall. What must be done to recover from stall is to lower the angle of attack and make the aircraft fly again by putting all the forces in balance. Let's watch the stall develop from above this airfoil. Note that the stall begins, at least on this shaped wing, near the fuselage. This is due to the wing twist, or washout as it is called. The pilot would begin to feel the effects of stall before it reaches the control surfaces. But if he didn't heed this warning, or a properly working stall warning horn, the turbulence would work its way out until the entire wing is stalled. While we're looking at the top of a wing's aerodynamics, note that air from under the wing tip tends to work outward and toward the top of the wing as it leaves the airfoil. At the same time, the air above the wing is deflected downward. The air mass tries to balance itself. This is of considerable consequence because it sets up violent whirlpools of air called vortices, and one of these disturbances could last for as much as several minutes in the air. A vortex like this one is an invisible hazard, especially around busy airports where large, heavy aircraft form them during takeoff and landing. They are the reason we always try to avoid the known paths of large, heavy, arriving and departing aircraft. Flight maneuvers create factors for the pilot to consider. For example, an airplane in a tight turn adds impressive centrifugal forces. The forces are out of balance in such attitudes, and the pilot must adjust to them accordingly. Turbulence, too, is an outside factor seriously affecting the aircraft's aerodynamics. But these are whole subjects in themselves and should be reviewed extensively by pilots as part of their continuing self-training. What we have seen is, of course, by no means the complete aerodynamic story. It's only a beginning to be added to by experience and reviewed throughout a pilot's flying career. The better a pilot understands the basic aerodynamics of flying, the safer he will be able to fly. And knowing how airplanes fly is essential to the skill and enjoyment of flying.